So today we're going to be finishing up the carboxylic acid derivatives chapter. By the end of this lecture, you should be able to say that you can explain and predict trends in reaction mechanism among a set of nucleophiles by applying your knowledge of relative nucleophilicity and basicity. You should be able to say you can draw mechanisms for acid and base catalyzed acyl substitution reactions with amides and nitriles. Predict the product of addition of C nucleophiles to esters and acid halides, and predict the product of reduction reactions of carboxylic acid derivatives with lithium aluminum hydride and acid halides with sodium borohydride. Amides are much less reactive than esters, but the mechanism for their hydrolysis is the same. You need to note that catalytic acid is not sufficient. You need one equivalent, which is 1 mole of the acid per mole of amide. And that's because the equilibrium is actually driven to completion by forming an ammonium salt. This is the driving force for this reaction. So this reaction is using HCl, and that's aqueous. So we need to start by protonating water. We're in acid, so next we're going to activate our carbonyl. Now water's going to add. Now we need to adjust our protons, so we'll deprotonate. Next we need to activate our leaving group. Then we kick out the leaving group. We use our lone pair on oxygen to help. Finally we deprotonate, and that provides the driving force of the reaction, the formation of this salt. We still have chloride in this flask. Next, we're going to look at the base-mediated hydrolysis of amides. So in these reactions, a couple of key things to note. Base-mediated amide hydrolysis needs forcing conditions, which means that we're using a lot of heat and a strong hydroxide nucleophile. We cannot kick out an N- derivative because the pKa of the conjugate acid is 35. That means that this N- is exceptionally basic. Okay, it's too high energy to form that in the presence of water. So we'll have to use a new trick in the mechanism where we use hydrogen bonding in the final step. So with that in mind, let's go forward. We're going to start nice and simple like we usually do. We have our strong nucleophile already ready to go. We add that directly to the amide. Here's a place where things get different already. We cannot just directly kick out a leaving group at this point because we have this NH- problem, right? If we were, I'm going to use red arrows to show what we're not going to do. We cannot reform the carbonyl and then kick this out because we have a couple of problems. First of all, this carboxylic acid is too acidic. We're forming this in a solution that has a lot of hydroxide, and hydroxide's pKa is about 16, so the reaction will lie irreversibly toward the carboxylate. The other problem is this one where the conjugate acid is pKa 35. Again, water is pKa 16. This is a 20 pKa unit difference. Okay, so that tells us that cannot be formed in the same flask. Anything with a bigger gap than 10 is going to be a problem. Okay, so this route here is all the no. Too acidic. This one, too basic. So what are we going to do? So we're in a solution with concentrated sodium hydroxide. So we have a lot of hydroxide around. We can go ahead and use another hydroxide molecule to get to this dianionic intermediate here. And now in this intermediate, our lone pair on nitrogen is no longer involved in a resonance interaction with this carbon, remember up here, the lone pair is in resonance with the carbonyl, so it's not available to be protonated. But here, this lone pair can interact with a proton donor. Of course, we don't have a good proton donor, but we do have a hydrogen bond donor, which is water. And so what will happen is you start by forming a hydrogen bonding interaction in this intermediate. And then in the next mechanistic step, the lone pair can come down, and instead of giving the electrons directly to nitrogen, we can actually just draw them getting this proton and kicking out hydroxide, which is a much more reasonable leaving group because we're already in a solution of hydroxide. So hydroxide is fine to form. So now we get to the carboxylate and the amine. And so this is where the reaction is going to sit. The carboxylate is not electrophilic. The amine is not going to add back this way. So this is the rate determining step of the reaction. It's really difficult to kick out this nitrogen, but once it happens, that's it. The reaction is not going to be reversed, and we'll have our carboxylate. Now, in a separate step during workup, we can go ahead and do the protonation. You'll want to note that we don't always write the workup, but that doesn't mean you don't need to put it in your mechanism. So one of your jobs as a budding chemist is to realize that you can't just isolate at the carboxylate stage if your product you're trying to get to is the acid. So you're going to need to provide this proton with the workup if it's not provided in the problem. So don't forget this. Okay, so this is a pretty tricky mechanism just because it does deviate from the pattern we've been looking at. So you want to make sure to spend some time with this and make sure you understand all the steps and why everything's happening so that you can remember it. So now we're going to look at hydrolysis of nitriles in either acidic or basic conditions. So in the first example, we're going to use acidic conditions. So again, you need to take note that this HCl is aqueous, and so you're going to start right away by making H3O+. Okay, and the next question you should ask yourself is, what is the most basic atom? Why are you asking that? Because you're in a reaction full of acid, and so if you're in a reaction full of acid, you need to find what is the base that's going to react with it, because that's the reaction that's going to be happening. Okay, so our most electronegative atom here is nitrogen. It's also the only atom that has a lone pair, so that makes the decision a little bit easier. You were pretty much stuck with either the nitrogen lone pair or the pi bond, but the lone pair is going to be more basic than the pi bond. So now you can go ahead and do the deprotonation of water and draw the product of those arrows. Again, if you remember to draw the byproducts of each step that you're doing the mechanism of, you'll have a clue for the next step right away. So we have water, that's going to be our nucleophile, and of course you know that we're trying to make some CO bonds. So it makes sense that we're going to want to add water. And the question you might have is, where does the water add? Here we have nitrogen that has a plus on it. That looks really tempting, right? But the problem is, nitrogen only has 4 orbitals, and they're all involved already in bonding interaction. So there's no way for this to come in and attack that nitrogen. But if we look at the resonance structures, you'll see that in the resonance form, the carbon has a plus on it. And in the form where it has this plus, it has an empty orbital. So that tells us that we're going to be able to add to this carbon. Okay, so this is another reminder that if you're getting stuck in a reaction, it's always a good idea to try and draw resonance forms, because the main structure tells you about the dominant form or what the molecule looks the most like in reality. But the minor resonance structure is going to tell you about the reactivity. Okay, and so the carbon here is electrophilic. When we do this with our reaction arrows, we draw these arrows at the same time, just like when we add to a carbonyl. So we get to an intermediate like this, and of course the next step is going to be to adjust our protons. So to do that, we'll use water. So then we'll draw the product of those arrows. Now here's another place where students sometimes make mistakes. So you're going to need to protonate the nitrogen, and the way to remember that is to look at the resonance forms here. So we can push our oxygen lone pair, and we can push this way onto the nitrogen, but that's going to give us an N minus, and we just talked a lot in the last video about how N minus was way too basic to form even in water, but now we're in a strong acid, and so this resonance structure is really not a major contributor. So, but it tells us that the nitrogen is going to want a proton. Okay, so that's how we're going to remember that we need to protonate the nitrogen before we can start to do something to get our carbonyl that we need. So in effect, we're activating our imine here for nucleophilic attack, just like we would activate a carbonyl. But it's the resonance structure that we're going to actually think about using. So you would get credit for doing this next step on either of these two structures because they are resonance forms. They represent the same molecule. I'm going to draw it on this intermediate because I think it's a little bit more familiar to you to be adding things to a carbonyl than to be adding to the iminium ion. So we're going to have water attack and give electrons to this oxygen. If you wanted to draw that on the other resonance form, it would be what I'm about to do in blue. So as you can see, you still are attacking this carbon and you're still giving electrons eventually to the nitrogen, either during the resonance step or drawing the resonance or during the actual attack. So whether you choose to draw the resonance structure and have water attack the resulting activated carbonyl, or whether you have water directly attack the iminium, is just up to you, whatever is most comfortable for you and helps you to think about the mechanism. In reality, it's water adding to one structure, and we're going to get to the same product either way. So now we're going to adjust our protons. So in the next step, we need to activate our leaving group, which we can do with the H3O plus we just made. So we'll kick out our leaving group, and that'll give us the protonated form of the carboxylic acid, which we can just deprotonate using water to get to the product. So overall, the mechanism is just like when you do the hydrolysis of an amide, except that you have an extra activate, attack, and adjust step. In the base-mediated hydrolysis of nitriles, we encounter some of the same challenges as the amide hydrolysis. So I'll highlight those as we go. So starting out, we're going to take our hydroxide and add that to the nitrile. If you're wondering why I added that to the carbon, again, you can look at the resonance structure and you'll see that this is the resonance form of the nitrile. So next you're going to adjust your protons. So next we're going to deprotonate at this position. And then we'll go ahead and reform our carbonyl, and we will get a proton from water, and that'll get us to the amide. Now from here, we just follow the same mechanism as I showed you before, where we hydrolyze the amide to a nitrile. So when you're setting this up in a lab, if you're careful with the conditions, you can actually stop at the amide from the nitrile, or if you keep heating for longer and very hot, then you'll be able to hydrolyze all the way down to the carboxylate, and then upon workup you would get the carboxylic acid. So just for practice, I'll show that mechanism again. We deprotonate again, and that's going to give us the species with 2 O minuses and the NH2. And now we'll need to activate that NH2 for leaving by forming a hydrogen bond. And so we'll reform the carbonyl and then get that proton. And this is what is going to be hanging out in your flask until you cool the reaction down, and probably even put it in an ice bath and then add aqueous HCl, and that's going to do the protonation step. To give the carboxylic acid. So with the nitrile hydrolysis, there's 2 possible products. One would be the amide, if you don't leave the reaction as long, or if you want to get all the way to the carboxylic acid, that's also an option. Okay, next kind of nucleophile we're going to look at is adding a strong nucleophile like a alkyl lithium or a Grignard reagent to an ester, and this proceeds exactly like with a aldehyde or ketone, with the exception that now there's a leaving group on your carbon, and so you have to contend with kicking out that leaving group, and when you do so, you form something that can react again. Okay, so that's the key challenge here, is remembering that you're actually going to add twice. And even if the equivalents of the reagent are not specified over the reaction arrow, the reaction is still going to proceed multiple times. So let's take a look. We're going to add our nucleophile to the carbonyl. That's going to give the alkoxide, as shown here. And now we can use this pair of electrons to help us kick out our leaving group. So that'll get us to an intermediate like this, where now our lithium that was the counterion for the alkoxide is still going to be coordinated to this carbonyl, and that's going to actually serve to further activate it. And so in reality, because of that and the fact that ketones are more electrophilic than esters, we're going to get very fast addition of the second equivalent. And this is the status in your flask until you, of course, do an acidic workup. There are a variety of ways you can do that, and this is going to lead to the formation of a tertiary alcohol. So just to reiterate a couple of key points, even if you use only one equivalent, the reagent is going to add twice. So this is going to result in a mixture of the tertiary alcohol, the ketone, and the ethyl ester. Second, the second addition of your alkyl lithium or your Grignard reagent is faster than the first. That's because ketones and aldehydes are more electrophilic than esters. Finally, you need to add aqueous acid to get the product alcohol. So this is just like when you do Grignard addition to aldehyde and ketones. If you were asked to provide the reagents, you would list 1 methyllithium THF and 2 H3O+. So here's something I know will drive you crazy, because everyone seems pretty frustrated about cuprates versus Grignards and organolithiums. But the key here is that cuprates are less reactive and they don't like to react with carbonyls. However, because acid chlorides are very reactive, you can react a cuprate with a carbonyl. And the nice thing here is that this gives you the product ketone, which you cannot access by adding methyl lithium or methyl Grignard to an ester derivative. So this will arrange itself as I've drawn here. Essentially, the oxygen atom will interact with the positively charged lithium, which you can draw with the plus on O, as I've done here, or you can draw the lone pair and a dash, 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 and lithium plus. They're kind of similar to resonance forms, just a matter of semantics there. So I prefer to draw it this way because it helps me see that what I've done here is activate my carbonyl. And so now the methyl group will be delivered in a pseudo intramolecular fashion to this carbonyl, resulting in this tetrahedral intermediate. And then we just kick out our chloride to get to the product ketone. So a couple of key points. First, coordination of the lithium with oxygen is going to help deliver this Gilman reagent to the carbonyl, allowing this methyl to be delivered in a pseudo intramolecular reaction that's going to be faster. The second key point is that Gilman reagents don't react with carbonyls, and so we're not going to get an overreaction where the product goes again to give an alcohol. The last point is that the byproduct is a copper 1 salt, which will react with air. And so if you're ever doing this in the lab for real, you want to keep that in mind and not do things like use air to dry your flash column that has copper salts on it, because I can tell you from experience, you might blow up that flash column and end up with pieces of glass in the hood behind yours. On the last couple of slides here, we're just going to talk about some reduction and oxidation chemistry. So all of the ester derivatives can be reduced to alcohols with lithium aluminum hydride. And you should be able to easily draw the mechanism for that yourselves. And so give it a try, and if you're having a hard time, then ask a question. Additionally, sodium borohydride, which is a weaker reductant, can react with acid chlorides to give the aldehyde, and it can react with aldehydes and ketones, as you already know. And so acid chlorides can be converted to alcohols with sodium borohydride. That's handy because if you have one ester and one acid chloride, that allows you to react just the acid chloride to get to the alcohol. When we react amides, either a tertiary amide or a secondary amide with lithium aluminum hydride, then we're going to access the corresponding amine. Again, this is something that you should be able to predict by drawing the reaction mechanism. It's going to proceed analogously to the hydrolysis of amide, so give that a try as well. Finally, nitriles can also be directly reduced to the amine by treatment with LAH that proceeds through an imine intermediate. On this last slide, we just have a chart that the book provides for the interconversion of carboxylic acid derivatives. And so if charts help you think about things, then this can be a handy tool for you going forward. So the way that you can use this is to basically see if you can predict reagents that are going to allow you to follow each of the arrows that are shown. So can you take an acid chloride and convert it to an anhydride? Can you convert the chloride to the ester, to the amide, or to the carboxylate? Similarly, can you convert the anhydride to either an ester, an amide, or a carboxylate? Can you convert an ester to an amide or a carboxylate? And can you convert an amide to a carboxylate? Remembering that once you form the carboxylate in your solution, you're going to need to react with a protic acid to get to the carboxylic acid. And from there, you're going to react to form the acid chloride. So you should be able to provide reagents for all of these arrows and also understand where these carboxylic acid derivatives fall in terms of their reactivity, and also be able to place an aldehyde and ketone into this chart.